think we've got everything fired up. I think that technology is going to cooperate. So with that, I know for most of you it's been like weeks since I've seen you. Joke. We just had class 10 minutes ago. Right. No, we get it, Dr. Mike. That was just a really painful joke. For the folks who just walked in, welcome. I'm glad to have you here. I think I said this during the last lecture as well, but I'll say it again. I think you're going to find this class to be really, really enjoyable. It's definitely material that you can sink your hands into. One thing that I didn't mention during the last class, which I think is worth mentioning because I think this matters, the math and the computations in here are really pretty basic. It's a lot of add, subtract, multiply, and divide, pretty basic stuff. Other than units, this stuff is really, really straightforward. I hope you enjoy it. I think, like I said, you'll find some stuff that you can really sink your hands into and really come away with some valuable stuff. A couple quick announcements. So office hours, same as what I mentioned last time. So I have office hours Monday, Wednesday from 1 to 3, on Thursday from 10 to 12. Tuesday, I'd say by appointment. I don't have class on Tuesday, so there's a chance I won't be here. I will go ahead and tell you that I will be here tomorrow. We have our technical conference on Thursday, so I'm going to be pretty busy getting all that stuff set up. If they're, first off, I'll say two things about the conference. If you are interested in volunteering or participating, we would definitely welcome it. One thing I'll say about that is it does put your face in front of potential employers. So there is, I understand that if you need a little bit more than an altruistic reason for doing it, then there's that, because there's some chances for networking there. So we really would like you to come. It's free for students. If you are going to come, I would ask that you register, just so we have a head count for how many people are there and so on and so forth. We do also distribute resume booklets to the potential employers. So if anybody is interested in having their resume included, we kind of need that sooner rather than later. And the conference is on Thursday, so you can do that. You can send that to either me or Austin Linville, who's our chapter president. Okay. First homework is coming Friday, so you're good for today. You don't need anything. Also, I'm curious, show of hands, who all got their manual, or it's coming? Okay, good. All right, you won't need your manual today. You won't need it for like the first week. But I will say this: the one statement I'll make about the manual, we will use this manual somewhat religiously during in-class examples. I know it's a weird, awkward size. Bring it. Just bring it to class, because we will use it. So that's sort of all I'll say about it, but just make sure that you have it. We won't need it for the first little bit, so you're definitely good there. Okay. Let's go ahead and jump into the notes, and I'll pull up the syllabus and pull up Blackboard and show you a couple things now that everything's working, and we'll get through some logistics. Okay, right off the bat, that is a typo because there is an attendance grade. Apologies for that. There we go. That's a little better. Okay. So the grading in the class is attendance, and then the homework, and the 3 exams. Now, one thing that might come across as kind of strange is that the exams are not equally weighted. There's a reason for that. This exam, so one of the things I say in a lot of my classes is that the exams are not intended to be comprehensive. Well, if there's any one class where I practice what I preach when it comes to that, it's this class, because they really aren't comprehensive in here. I mean, sure, you need to know what FY is and FU is for various grades of steel, but you can look that up. There's very, very little material that bleeds over. We test on a topic, then we move on to another topic, and then so on and so forth. When it comes to the 3 exams are split up based on the topics that we cover. So the first exam is on tension members, block shear rupture, fundamentals, takedown, so on and so forth. And our second exam is on connections. It's on bolted connections and welded connections. And all the stuff that we do in here, bolted and welded connections are pretty easy. So it's a pretty straightforward exam, and as a result, it's not really worth a lot because it's hard to make that stuff challenging. The final exam, however, is the one that's the toughest. Like, I'll go ahead and tell you, like for concrete design, for those of you that are in there, I'd say the toughest exam is probably the second exam. In here, it's the final. I'll go ahead and tell you. So the exams are weighted appropriately. Okay, so that's point one. Point two, let's talk about the kind of textbook for the class, which is this. So everybody in here should have gotten a copy of the coupon code that I emailed out for the AISC manual. Most of you have this on its way. I emailed this out, and then I also listed some sort of FYI, FAQ answers to some questions that I typically get. Do I really need it? Yes, you do. Can I borrow it from a friend if I don't want to buy it? Absolutely. It's just got to be the blue one, okay? These come out regularly. We're on the 15th edition, and so it's got this sort of turquoise blue type color. The one before this was like maroon, like a burgundy red. The one before that was black. It's got to be this one. They change enough from edition to edition that it would affect our answers. Now, this is the third or the 15th edition, and yours is probably like, I don't know, the second or third printing. Mine says first printing. That doesn't matter. They just reprint them every year. But as long as you have a blue one, you're good. Okay, I don't care if you borrow it from a friend, whatnot. But you do need your own. Okay, you can't like, oh, well, me and my friend want to buy one to borrow. No, you got to have your own because we use these on exams. Okay, so you need your own copy. Now, I want to show you something else that's going to pop up in the lecture notes. And that's this, okay? If you start flipping through the lecture notes in this class, you're going to see a green star pop up on various slides. Those green stars refer to these, okay? There are various sections in the manual that are worth putting a tab on, or like a sticky note or something like that, okay? Because we're going to use a lot of stuff in this manual, but some of it we're going to use a lot, okay? So like for instance, when we get to beams, the ZX tables, we're going to be using the ZX tables a lot because there's a lot of really important critical information for a beam. The anchor points, the BF, the plastic moment, reduced yield moment, you all know what I'm talking about later. But it's all here, and so this is a really, really valuable resource to find that. The beam charts, the bolt tables, the shear lag factors. And so having like a ready access to this stuff is really important. Now, as we go through the semester, you'll find tabs. I'll say, okay, you need to put a tab here because we're going to reference this. I do get a common question right about this point, and somebody will usually ask, hey, Dr. Mike, can we just see your manual so we can tab it all now? I will do that if you want, but I don't recommend it. The reason why I don't recommend it is because for exam 1, we may use like 3 or 4 of these. Then exam 2, we might use 6 or 7. Then exam 3, we might have 10 or 12. And so if you tab it all at once, you take the first exam, you got 20 tabs to sort through where you only needed like 3 or 4. You see what I mean? It really does make a lot more sense to tab as you go, okay? But, I mean, if you want to see it, you're more than welcome to. But again, I'm making a point to reference this stuff as we progress forward, okay? Sound good? All right. So again, it's probably not a bad idea to get you some sticky notes or a label maker, whatever you think is appropriate. Attendance, I am going to take attendance. I believe that I started passing. Did I get the sign sheet passed around? Okay, good. I'm going to go ahead and hand out a copy of the syllabus. 1, 2, 3, 4. There you go. 1, 2, 3, 4. 1, 2. I'm going to record the lectures like I have been. This one should be recording. One other note, I haven't totally made up my mind, but a while back I used a somewhat nicer clip-on mic, and it sort of burned out on me. Last semester I tried this other one. I don't think it worked out very well. I ended up using the ambient mics, and it does sort of sound like an echo chamber. So I think I'm going to probably get another one of those nicer mics, and hopefully, I haven't totally made up my mind on it because they're kind of expensive, but I think I might bite the bullet and go ahead and do that. I will keep you posted. Blackboard let's talk about Blackboard. I will use the Blackboard course content and grade pages pretty regularly. Make sure and check that. I'm going to pull up Blackboard here in a second because there's a couple things I want to show you. Let's talk about homeworks and exams. I have 8 homework assignments in here. They all cover various topics, like sort of like modular topics. Like homework 2 is on tension member analysis. Homework 3, tension member design. Homework 4, bolted connections. Homework 5, welded connections. Like they all cover various topics. Do me a favor, don't turn those in late. But you all are seniors at this point, shouldn't really be a big deal. I want a cover page. You could use the original assignment if you want, but I want a cover page on there. I will have 3 exams. I'll have exam review days scheduled. I'll pull up the schedule here in a second. Remember, for those of you that are also in concrete design, other than the last homework assignment, homework assignments will not be due on the same day, and exams are not during the same week. So I might have an exam in week 6 in steel design and week 7 in concrete design. So I make sure not to have 2 exams on the same week. I don't think that does you any good. I will give you the opportunity to use a formula sheet. You can put whatever you want on that formula sheet except for worked out examples, but you also get to use this during the exam as well. So don't waste time putting stuff that's in here on your formula sheet. And you desperately need this for the exams. Because if I say, okay, you have a beam that's a W10 by 49, you need to know what the moment of inertia and ZX and all that stuff is. It's in here, okay? So that's what this is. Okay. Let's see. Any questions so far? Okay. Let me pull up the syllabus real quick. Most of what I just said is in here. Like I said, there is no textbook, but there is the manual, and you do need that. Grade distribution, you all know the drill on all of this. Here's what I wanted to pull up. So Wednesday, January 29th, I will not be here. I have a research trip that I got to go to, so that class will be canceled for sure that day. First exam will be Wednesday, February 19th, and the second exam will be Wednesday, March 18th, which is right before spring break. And I've got the schedule set up in here to where we'll have a makeup day here, and if we don't need to use that lecture, we won't. You'll get the Friday before spring break off. I'll go ahead and tell you that is probably not going to be the case in concrete design. We have homework due that day, and I got to see where we get from a lecture standpoint. There is a chance that we can cancel that day, but it's not high. I'm just being honest with you. So just something to keep in mind. But in here, we're probably definitely going to do that. When we come back from break, from spring break, I'm going to have April 3rd canceled because that's the Virginia's conference, the canoe and the bridge. So I'll be gone then. And then we have our final exam on April 28th. We have our, for finals week, we have the concrete final Monday, the steel final Tuesday. So we get to get those like a Band-Aid, get them done. Okay? Like I said, the final homework assignments for both classes are due that same day, but other than that, everything's staggered. Excuse me. So far, so good? All right. Let me pull up Blackboard real quick. So I have the Blackboard pages pulled up for both classes. So this is steel design, this is concrete design. When you go to course content for steel design, you'll find the syllabus here. The old homework assignments, I'll post solutions to the homeworks as we do them in this folder. So if you had me for class before, that's typically what I do. For lecture notes and supplements, right now I've got enough at least to get us through the first week, and the same thing's true in concrete design. So for instance, if you go to concrete design, go to course content, lecture notes, same story. I am going to post a few design aids and supplements in here as the semester progresses. I want to show you what I've got here, these AISC resources. So let me just sort of back up. This manual is written by the American Institute of Steel Construction, AISC. Okay? They are basically the governing body that designs and writes the specifications for how to design steel structures in the United States. That's what they are. The American Concrete Institute is a similar body for concrete structures. We talked about that in concrete design in the last class session. I will be perfectly honest. and ACI can get a little mad at me, like, comment, and subscribe. But I will go ahead and tell you that I much more prefer, as an educator, working with AISC, because they do a really good job of making their materials available for free, okay? Not all of them, but some of them. For example, while the manual is not free, there are two things that are, okay? The first is this PDF. See where it says A360-16 spec and commentary? Okay, let me show you what that is. So I've got this pulled up here. This is the document that delineates how to design structures in the United States. Now, it is printed in your manual. If you have the manual, you can tell where it is. It's in the back because there's like these gray line pages, and then there's a chunk of pages in front of it, okay? I'm going to show you something about that here in a second. So, what those are basically the code and what's called the commentary, okay? And this is going to be something that I want you to become a little bit familiar with when you all start getting into the real world. Because the code will tell you what you're supposed to do. The commentary will tell you why you're supposed to do it, okay? Now, I really like how the steel industry organizes their spec because they put the code in one section and the commentary in the other. Some folks, or some specs, they put them side by side. I've never really liked that, but it is what it is. But let me show you sort of how this works. So let me scroll down a bit. So, let's see, right here. Chapter D, Design of Members for Tension. We'll be looking at this very, very soon. This is the section that tells us how we design steel elements that are being yanked on, if they're in tension. And Chapter E, for example, is Design of Members for Compression, if they're being pushed on. So there's different equations, different specifications for all of this. Now, Chapter D tells you what you're supposed to do. It tells you what the equations are, what the safety factors are, what all the various shear lag factors that you need to know, et cetera, et cetera. If you fast forward a bit in the spec, you'll start to see these like gray line pages. See the ones that have the gray on the side? And if you look, there is a similar Chapter D of Design of Members for Tension. And for every one of those sections that were in the code, this has a more in-depth explanation as to why those equations are what they are, okay? I'm telling you this now, not really so much for what you need to know on day one in CE 314 at Marshall. I'm telling you this for your careers, because many codes are like this, whether it's the bridge design spec or you highway folks, the green book or whatever. There's plenty of instances as a practicing engineer where you've been given a document and it's like, well, I don't know why this is what it is. That's what the commentary is for. It'll tell you what the reasoning why the equations are what the equations are. So I'm just telling you that document is on Blackboard, so you all can download that today. And that is basically, here, hold on. So that is this part of the manual right here. Like this gray part's the commentary and the code, okay? So you could download that as a PDF right now, all this part of the manual. The other part that's uploaded on Blackboard is this Excel sheet. See where it says AISC Shapes Database? You're going to think this is silly, but let me explain what this is. So when you download that, you're going to get a disclaimer, and then you're going to get this. Let me zoom out a bit, sort of. Yeah, it's pretty big, right? This is the dimensions and details for every steel shape available in the United States, okay? We're going to talk about how to interpret this data and how to understand it throughout the semester, but this basically lists all the dimensions and properties and so on and so forth. Now, this information is actually in the very front of the manual. Like if you open it up to the first few tables, like you'll see these sections on WTs and angles and HPs and W shapes and so on and so forth. It's all here. This is just taking that data and dumping it into Excel, okay? And so if you're looking at a given shape, for example, let's make one up. Let's look at the 16 by 40. So the 16 by 40 weighs 40 pounds per foot. It has a cross-sectional area of 11.8 square inches. It's 16 inches deep. It has a flange width of 7 inches, a web thickness of 0.305 inches, a flange thickness of 0.505 inches. All of that information's in here as well, but this is all just in Excel. So if you want to download that and have it on your laptops or whatnot for when you're doing homeworks, that's fine too. They put that on the website and it's available for free. I also recommend that you all develop or sign up for an AISC student membership. It's free, and they have like oodles and oodles of design guides that you could download for free. And if you had to pay for those things, it's like $1,000. So it's like $1,000 of free stuff. I like free. I don't know about you, but that's okay with me. But I would consider that. Plus, being an AISC student member looks good on a resume. All that jazz. Okay. All right. Any questions? My goal is within the next couple weeks to fully populate the Blackboard of both classes. Hopefully I'll have everything uploaded for both classes, like all the lecture notes and everything. I got a couple things in concrete design I got to update because we just developed a new specification, but other than that, we should be good. Okay. So far so good? All right. So during concrete design, which, by the way, I might reference concrete design here a little bit. I think I'm actually in a good place with this group to do that because everybody in here has either already had concrete design, right? You two, and I think somebody else has already had it, or are in it now. So I can reference that pretty easily. So that's pretty good. And I tried to make sure that I'm not doubling up, that I'm not saying the same stuff in both classes. So in concrete design today, we talked about reliability and allowable stress design versus LRFD and all that. Today I want to take a little bit more of a higher level approach and talk about project development because I think it's important in what your role is as a structural engineer. So what is our role as a structural engineer? Let's say Geico wants a new corporate headquarters. They're willing to put whatever money that's necessary to build that corporate headquarters. How does that go about? Well, Geico contacts a developer or an A&E firm. A&E stands for architecture and engineering, right? So they contact them, and now what their job is to interpret the desires of a client and turn that into a reality. Everybody jokes about architects like, they just, figure out the color paint on the walls and make everything look pretty. They have a very difficult job because they have to take an abstract concept from somebody who has no idea about engineering or building construction or anything like that and turn it into a reality. That's challenging. Our job is just as challenging because our job is to then take that design and make it structurally sound and make it work. That's our job as a structural engineer. So what are our tasks? Well, we need to meet the aesthetic demands of both the architect and the client, because typically the way this works is that we work for the architect, right? We work for the architect and the architect works for the client. So we're like a sub to a sub usually in a lot of this. That's shorthand for a subcontractor. So we are a subcontractor to the architect and so on and so forth. Obviously, we need to meet structural strength and safety. It's got to be safe. It's got to hold up the load so it doesn't kill people. One of the other things that doesn't really get talked a lot on day one in structural engineering is serviceability. So later on, we will talk about the concept of a limit state. And a limit state is just a condition that we define as important for a structure. In other words, if we fail that, then we have failed the performance that we need to redesign. Otherwise, we're good. We have two really primary classifications. We have strength limit states and service limit states. And strength limit states are, if you put more load than this on it, structure's going to fall down and kill people. But service limit states don't really address that. They're more like the structure needs to not vibrate too much, otherwise it will be uncomfortable, or it can't deflect too much, or otherwise it will be seen as poor behavior of the structure. Like it's intended to govern day-to-day performance of the structure as opposed to the worst-case scenarios. And so that's important as well. And we'll have some instances of service limit states very, very soon. So we'll get into that. Constructability. Engineers for a long time have gotten a bad rap of designing these Swiss watch, weird, complex structures that nobody can actually build because they're too damn complicated. And so that's really important. In fact, if you're designing a bridge, it's the engineer's responsibility to design a bridge that is constructible, like that's actually delineated in spec. Also, in the end, it's got to be economical. It can't be designing a structure that's super massive beams, super thick flanges, and so on and so forth, and it's going to cost an arm and a leg. it has to be effective from an economical standpoint as well. There's a famous quote from a guy named Hardy Cross that said, strength is essential and otherwise unimportant. In other words, once you've met the fact that the structure is safe and isn't going to kill people, there's a whole lot of other stuff that we have to consider as well. Hardy Cross is a very famous structural engineer. He came up with some very refined analytical tools that were the mainstay until a guy named Bill Gates came around and said we can do this a lot better and develop the means to integrate some computational tools into what we do. Before Bill Gates, we would have been talking about Hardy Cross a lot more. So what's your role as a structural engineer in the project process? Well, let's talk about this from phases. So the first step is the definition of the project, the planning. Geico Insurance wants to build a new corporate headquarters, or whatever company, whatever developer wants to build a project. So what's the role of the structural engineer? Well, they're trying to determine the function of the building, the general layout, the design criteria, just trying to figure out what's going on. I mean, if you're designing an office building versus designing, let's say, a hotel, the design from a structural engineer standpoint gets different right then on day one. See, for example, if you're designing a hotel, typically with hotel designs, you know where the hallways are and you know where the rooms are, okay? Like the hallways are here and the rooms are there. And that's important because there are different loads that we apply on the hallways than we do on the floors. There's typically more people on any average time in the hallways than there are on the floors, which is why hallways tend to have like 80, 90 PSF loads and the rooms only have 50 PSF loads because there's more people there and they need to be able to handle that in the instance of emergencies, fires, so on and so forth. So we have heavier loads in the hallways. Whereas if you're designing a commercial office building, it's a little different. See, how many of you have ever been like in a large office building, one of those commercial spaces where people can rent out, square foot and put whatever in there? If you're the developer, you want your tenants to be able to arrange that floor space however they want. Like if here's the building, like let's say here's your building, and I got a dentist's office that wants this space, I got an accountant that wants this space over here, I got a law firm that wants this space, the Social Security office wants this space, so on and so forth. As the developer, you want that building to be as versatile as possible. So what I, as the structural engineer, might do is I might design that floor system as if it's all one big hallway. By designing it as one big hallway, it doesn't matter whether the hallways are. You can do whatever you want, right? So that, right off the bat, understanding what you're designing matters. Understanding the risk category of a structure. That's something we're going to talk about later. Different structures have different level of risk categories, which affects the loads that you use. Here's an example. A risk category 1 structure would be something like a grain silo or an unmanned warehouse. Whereas if it falls down, yeah, it sucks, but it's probably not going to kill anybody because there's nobody there. Whereas the highest level, a risk 4 category structure, might be something like a hospital or a police station or a fire station. Because if that falls down, not only does it put people in the building at risk, but that puts the community at risk. What would happen if the structure of St. Mary's just failed? You know what I mean? That would affect everybody in the city, right? Because then there's no hospital, right? So the risk category for that structure, and as a result, the loads that we have to use are much higher. In other words, I might design this building for 115 mile per hour winds, but I might design that one for 180 mile per hour winds because that better not fall down. You know what I mean? So that matters. And so right off the bat, understanding that stuff is important. There are also business aspects, pre-contract negotiations. People need to understand the schedules and fees associated with the work, the scope of responsibilities, how things are going to get communicated, and ultimately developing contracts. Then we get into preliminary configurations. This is where we get a more rigorous definition of the structural criteria, get into the loads and initial member design, just the main members and layout. It might get tweaked a little bit near the end, but it's kind of get a little bit of a better idea of how much this is going to cost. Selecting the optimal structure type. Does it need to be a steel building? Does it need to be a reinforced concrete building? Also, buildings tend to get built on the ground, so we need to understand the geotech requirements. Probably going to schedule some boring logs, get some soil data, try and get a bearing capacity, get foundation design, so on and so forth. Then we start tweaking this and refining it, getting our final design done, making our final analysis, the loads, evaluating and optimizing what it is that we're doing. And once you've got a final design, then we can start doing cost estimates. We've got 40 W10 by 49s, and each W10 by 49 is going to cost $2,000 once it's fabricated and drilled, and so on and so forth. So that's how much that's going to be. We need, 6,400 bolts for the project, or whatever, whatever makes sense. It's time to draw that up. We need to get some structural drawings, some construction specs, get the bid documents ready so that some contractor can go bid and build the thing. You might be involved in contract administration. Once you award that thing, you actually have to review its construction, review the bids, so on and so forth. What I have on this slide is something I really want you to commit to, not really to memory, but to heart. And I don't care if we're talking about structural engineering or geotechnical engineering or whatever. This is something I really want you to keep in mind throughout your career. What I have over here on the left is the ability to influence the cost of a project over time. And when you're in the beginning phases, the conceptual planning phases, the design phases, you have a really big ability to influence the cost of that project. Like, let's say we're in this room right now and we want to build a new corporate headquarters for Geico. We could have a discussion today as to whether or not we want to build a steel structure or a concrete structure. And that discussion could have a significant influence of the cost of that project at the end. That matters, okay? So you have a really strong ability to influence the cost of a project over time. By the time that you're fabricating the structure and erecting it, you're not really going to have that much of an ability to affect the cost because the decisions are made. But what about the flip side? What about the cost of the change over time? Us having a discussion about whether or not that Geico headquarters needs to be a steel building or a concrete building doesn't cost any money, right? But what if you're fabricating the structure and you go, whoops, those W10 by 49s needed to be W10 by 53s. That's going to cost some money. That's going to cost a lot of cash, okay? So when you're at the tail end of a project and you're needing to change things, that costs a lot of money. And so I just want you to commit this concept to your head, the idea that at the beginning of the project, decisions are cheap, but they also matter, okay? And that near the end of the project, if you're going to change something, it's going to cost, okay? And it doesn't matter if we're talking about structural engineering or transportation engineering. I just think this is important for you to understand as an engineer, okay? Does that make sense? Any questions on that? All right. I'm going to really quickly breeze through this. We talked about design philosophies during our last lecture, and if you've already had me for concrete design, you probably remembered this because we talked about the concepts of design philosophies. So one of our first philosophies is allowable stress design. The idea is that if I break this table and it fails at 800 pounds, what I might use is a factor of safety of 2 and say, no, you can only put 400 pounds on this before it fails. And that's great, it's a simple philosophy, but it doesn't take into account uncertainty. There are oodles of uncertainties associated with the material quality, how this thing was fabricated, how it was put together, how it was constructed. There are uncertainties with loads, snow loads and dead loads and live loads don't behave the same. They have different statistical uncertainties. And so what we do is we handle that through probability-based methods. So an allowable stress design method just takes the quantity and divides it by a factor of safety. We are not going to do that in here. However, let me be clear, factors of safety still get used appropriately, I might add, in certain areas of engineering. For us, I would say geotechnical engineering is the one where factors of safety are still appropriate because soil behavior is so variable. You could get a boring here, and literally go right here and get another boring and get completely different behaviors. Soil's just weird. It doesn't behave, as easily as you would think. It's so variable. And so in that world, because the variability is so high, it's screw it, let's just go with a factor of safety of 3. And I don't think there's anything wrong with that. It's just something to keep in mind. Now, load and resistance factor design is what we're going to use. So if you were in concrete design, you probably remember this. If you're in it now, you're going to become familiar with these very, very soon. The concept is that we factor not just our loads, but our resistances. A very common load combination that we'll use is 1.2 times the dead plus 1.6 times the live. You don't need to commit that to memory now. We'll use it, believe me, more than enough that it'll become valuable, or it'll become stuck in your head, I should say. The reason why we use a probability-based approach is because what we're trying to do is look at the structure from a probability standpoint, from a normal distribution. You know, if you recognize the normal distribution goes on forever. And so if it goes on forever and you classify structural behavior as behaving this way, you know, the resistance of a structure and its loads, there are some instances where the loads would be bigger than the resistance and the structure is unsafe. So the idea is, well, let's not try and design structures that are perfectly safe, because there is no structure that's perfectly safe. Instead, let's try and manage that probability of failure by developing load combinations that keep this small and uniform, hence where this is coming from. So here are some of our load combos that we use in structural engineering. These are the same ones from steel design and concrete design. Just to make sure that everybody's aware, all of these are on Blackboard as well. So if there's something that you miss, don't worry, I've uploaded all this stuff to Blackboard. Just about every problem that we do in this course is going to include either dead load or live load. And so these first two are really going to be ones that you pay attention to, either 1.4 dead or 1.2 dead plus 1.6 live. And so the idea is that for a given beam, it might have dead loads, live loads, snow loads, wind loads. The idea is that you would go through all of them and then just pick the one that generates the maximum response. However, in most scenarios, you don't have to go through all of them because some of them wouldn't make sense. Like, for example, let's take the beam up here. There are beams up here supporting the floor system above us, right? Up here are a bunch of offices. What do you think the snow load on those offices are? Has there ever been snow inside the building? Right? So the snow load inside would be 0. So think if I was looking inside the building, I could say, well, snow is going to be 0. Right? There's no wind or earthquake load inside the building, and we'll discuss why. So I propose to you that for interior elements, you can take the wind and earthquake load, so that equals 0. So the only thing you have to deal with is dead and live when you're designing interior elements, and that's either that or that. Because set everything else equal to 0, and these are the only ones that are going to matter. Like I said, we will use those pretty regularly, and you'll see where those are applied. You don't really need to memorize them now. Don't worry, you'll pick them up later. Any questions so far? Okay. Here's what we're going to do. In this course, I tend to focus on lateral load events. So there are 2 types of loads that act laterally on structures. So we have 5 load events that we typically consider in structural engineering. 3 of them act up and down. That's dead load, live load, and what? Everybody remembers from our last lecture? What acts up and down? Dead, live, and snow. Snow acts up and down. Rain acts up and down too, but typically rain you can drain off. And so rain doesn't stay on the building like snow does. As for loads that act left to right, there's 2 that we have to consider, and that's wind and earthquakes, seismic. In here, I like to focus on the lateral loads, and in concrete design, I like to focus on the gravity loads. So between the 2 classes, you sort of got a general understanding of everything. Now, I will go ahead and preface this by saying that lateral loads they're complicated. They can really get tricky. And lateral load design typically gets harder as the building gets taller. Like, it's easier to design this building for lateral loads than it is Smith. Because as buildings get taller, the loads increase. In fact, that's what makes tall building design hard, is the lateral events. So we're gonna, I don't want to say, the term watered down, I don't like the term watered down, but I want to say it's more of a fundamental approach to what you need to know to do lateral design, and then we're going to get into the manual. So you got more than enough time to get it. If you have not yet ordered it or taken steps to procure it, I would do so now, because by the time that we get back from, so we have class Monday, Wednesday, Friday. We're going to miss Monday because of the holiday, and we'll be back on Wednesday. By Wednesday, we're going to start using the manual pretty prevalently. One other final point, it's very, very minor, but I thought I would mention it. If you open the manual to like something like this, see how there's green numbers and there's blue numbers? The green numbers and blue numbers correspond to allowable stress design and LRFD. In this course, we're going to use LRFD. We use the blue numbers. Don't worry, I'll indicate that pretty clearly as we progress through the semester, but by and large, we'll be using blue numbers. So. Any questions? All right, so on Wednesday, we're going to start attacking lateral loads. What we'll do is, like I said, we've got two loads that we're going to look at, and that's wind and earthquakes. I'll explain the doggy picture later. But we'll start off with wind and go into how we assess that. So like, for instance, this is a wind speed map in the United States. Why do you think the higher winds are on the coast? What happens on the coasts that doesn't happen here? That would have to do with wind. Somebody said it. Hurricanes. Exactly. So you have higher wind speeds on the coast for the hurricanes and things like that. We'll talk about that. And how you actually break that down and compute that and so on and so forth. And then we'll get into seismic events and how you break that down as well. That's all I got. We'll see you.